Good day, I am Matej Mihelčić, and the goal of this presentation is to provide a short overview of a data mining field called Redescription Mining, and hopefully explain what is its connection to logic. So that is a application kind of presentation. Okay, so I will start the presentation with a I can actually move this. I will start the presentation by giving a formal definition of a field. Then I will try to compare it with some well-known fields in machine learning and data mining that you probably all know about, to see what are the specifics of the field, and then we'll go onward on explaining all these things that are on the slide. So formally, Redescription mining works with a set of instances, let's denote them I, a set of attributes A, describing these instances, a logical mapping W that maps these attributes to some views. They are denoted by numbers here. We have a query language. Here we will come to the connection with logic, some similarity relation, and a constraint set that we will call C. The task is to find all redescriptions that satisfy the constraints in this set C. And then I will, as I move on with the presentation, I will explain what are all these things. Okay, so first to the connection with the well-known approaches. So one of the most known approaches is that of a supervised learning. Probably all of you have heard about it. So the idea is to have a data set in which we have some instances and some attributes, and we have some target variable of interest. And we basically mostly know the values of these attributes that describe the instances, but we would like to know the value of the target variable. Then we take a data set and part of instances for which we know these values, and then we learn a model, machine learning model, that kind of captures the connections between these attributes and the target variable. And then the idea is to take some new instances and predict the target value for them. And then based on the type of the task, we can have the regression task if we want to predict some numerical value, or we have a general classification task if we want to categorize a subject into some category. In contrast to this field, we have also the unsupervised setting, where the goal is not to predict the value of some property of interest, but to basically structure the data in some way, unsupervised way. And the main methodology here is clustering. So it kind of discovers groups of highly connected instances in the data. Then again, we can have more complex data where instances are not described by only one, but more sets of attributes. And we would like to find groups of instances that are similar with respect to all these groups. This is also interesting in many applications. So we want to find a group that is connected with respect to one property, then to it at the same time with respect to another property. We can get this by doing multi-view clustering. And then we finally come to the main point of redescription mining, which, in addition to finding these groups that can be described by more than one set of attributes, also discovers some rules that describe these instances. So we basically know the properties that are valid for these groups. And then I will go into the details of what are the queries and how do we build them. So we get the groups and we also get some kind of description. So this is harder and more information that we get from the clustering. It is also different from something called conceptual clustering, because it can take into account more than one set of attributes, and it can take into account richer query language. Okay, so what is then a redescription? It is basically a couple of queries, and I will show what the queries are. And it describes some set of instances in more than one way. That's why it is called a redescription. It describes in multiple ways. So what needs to be true for this redescription? So each query must contain disjoint attributes, because we are interested in to observe the relations between these properties. And a good thing would be that they describe very similar or ideally the same subset of instances. So if we get several queries describing the same set of instances, then basically this redescription uniquely describes these instances and no other. This is a very specific property. Okay, so for the similarity relation, mostly people use Jacquard similarity because it naturally computes the similarity. It computes the intersection divided by the union and if the intersection and the union are the same, so it means it describes only these instances and no other. This is the best. And we have also in the constraint set, one of the more important measures are the significance of redescription. So basically, I try to compute how probable it is to get a redescription of with the support of this size or larger by randomly joining queries with some a priori probabilities computed like this. Okay, so what are the queries in themselves? So for redescriptions that work on Boolean data, these are formula of propositional logic. They contain conjunction, disjunction, and negation logical operators. So implications and equivalences are not present because they can be transformed into these ones. But we are also more interested in getting kind of what is truly valid in the data. So in that case, it is even more understandable to read rules that only contain these three. And here we can see one example of how this looks. So this is from the application where we have some bacteria and their phenotypes. So these are some kind of observable properties, and then you can have like their genetic structure, and of course bacteria that live in different environments evolve some special abilities that are actually visible in their genetic makeup. And then when you have a redescription like that, you can basically see what is the connection of some phenotype with their genetic properties, because some specific groups of genes occur here and some very specific phenotypes occur for this kind of bacterial species. Okay, so this is the most simple type of a redescription that only works on, so the algorithms that provide this only work on Boolean data, so every attribute can be only true or false. But of course, this is not enough. But for these redescriptions on Boolean data, we can also derive some theoretical properties. So there is this impossibility result that says that if we have a Boolean data with m attributes and we basically have all 2 to the power of m rows, so all different combinations, then we cannot find any distinct redescription. If we define a redescription of being perfect, as in describing the same subset of instances, because there will always be at least one instance that is not described by one descriptor, but is described by the other. But if we have at least one missing row, then these exact redescriptions exist. Good thing is that it also applies if formula are in conjunctive or disjunctive normal form. However, we must not restrict the number of attributes that we use in the queries, or otherwise it does not apply again. Of course, in practice, it is interesting to get as shorter descriptions as possible because they are more understandable. That's why in practice we usually use this loose definition in which we basically use Jacquard as similarity relation. We would like to find as accurate redescriptions as possible. Okay, so for the algorithms that work on the Boolean data, we have several of them. So cartwheels is the first one using decision trees, and then we have the approach based on relaxation lattice and closed item set mining, greedy approach based on frequent item set mining. I will just very shortly show some pictures. So on the cartwheels, the main idea is to construct targets for the instances in the data by observing some attribute from one of the views, and then we build a tree like so, and then we encode these leaves as some classes depending on the variables from the second view, and then we build a matching tree that actually uses attributes from the first view and target that are these encoded variables, and then the idea is to mesh them in the leaves and look at the paths from the one root to the another, and these paths ideally form redescriptions because these leaves should represent somehow related classes. relaxation lattice-based algorithms start from some very restricted formula, and then they relax it, so they remove some variables, they add these junctions, and then they look at the connections between these. The closed item set kind of algorithms, they try to find. They also relax descriptors, but these sets of instances described need to be different, and then they form a lattice and find the descriptions. Then we have this greedy approach, in which first two initial attributes are paired that are the most similar, and then atomically attributes are added that increase similarity between queries, so we get more complex and more complex queries. And then finally the output is a redescription. Then we have this approach with frequent item set mining, where first closed item sets are mined, then they are negated, and then they are combined with conjunction and disjunction. And this is an iterative process. So these item sets, which are basically sets of attributes, are combined. They are ranked, filtered, extracted, and then the final redescriptions are outputted to the user. So that's very quickly about the algorithms that worked on the Boolean data. However, as I said, Boolean data is not always enough to describe the objects that we see in nature, because it is hard to express some properties that are really numeric by using only Boolean data. It is possible, but it is imprecise. So for instance, we would like to put blood levels of our patients into the data. We would like to put the temperature, things like that, that are in nature continuous. So what we need to do to use that kind of things in redescription mining, we need to enrich the query language. So the query language here is enriched with some relational predicates like equal, less, greater, less or equal, and greater than equal. And then the queries basically have a form like this. So we also have some numerical values and the relational predicates, and then again we can determine what instances satisfy these queries and basically compute all these measures. Okay, so for the numerical attributes, no theoretical properties were studied, but of course one can always okay, for categorical data set, it is easily transformable to Boolean one, and then all the properties apply. But for numerical ones, one can always do binning and apply binning techniques. And then on these transform data sets, the properties will again apply. However, this is an inaccurate representation of the numerical data. So that is a bit more tricky. And of course, the amount of redescriptions we can obtain on numerical data set is not really finite anymore. Okay, and then there is the added complexity in the real world available data, and this is that some measurements can be missing due to various reasons, malfunctions of equipment, unavailability of the subjects, and things like that. And this also needs to be incorporated into the redescription mining. It can be either incorporated by extending the domain of relational predicates or defining the truth tables of logical operators. And then we also, based on how we handle these values, we get several different measures of similarity between queries. Okay, so for the algorithms that work with numerical, categorical, and missing values, there are two algorithms. One is the RRMI, created by the Esther Galburn and Pauli Miettinen, and the second one is the ClassRM, which was devised by me and my supervisors, Tomislav Šmuc, Nadal Vraćen, and also our collaborator, Saša Džerovski. This ClassRM algorithm basically works by building predictive clustering trees. So this is a different kind than a regular decision tree. So we can basically take multiple targets on this target side, which allows it to transform all these nodes into rules, use these rules as targets, and then obtain larger number and more accurate redescriptions that one can obtain only by looking at these leaves, which is possible by training the regular decision trees. And this process then iterates and has many things inside, but I'm not going to go into the details of that here. And then there is the approach which was published in 2021, which can basically take a mapping of attributes to an arbitrary number of views, which needs to be more complex because of this curse of dimensionality that we get by having more than 2 views. So basically one can create much larger number of redescriptions on this larger data set. Okay, and then there is the work in 2014 from Esther Galbrun and Kimming, which basically wanted to extend redescription mining not only to be able to describe properties of instances, but also relations between these instances. Their work allows using binary relations, so one can actually model properties like something is more expensive than something else, or something is a mother or of something else, or a child. So some kind of binary relations can be described as well. And that required further extending the query language. So now we have binary relations in combination with this equal, less, or equal, and so on, which are visible here. But usually these kind of queries are represented as graphs because they show the relations between objects in a nice way. The idea of redescription is very similar. So we take this query, which is a graph. We actually look at all the instances that satisfy this graph. We look at all the instances that satisfy the second graph, and then we compute the checkered similarity again. Okay, the algorithm works in following steps. So first, it represents the data as directed graphs. Instances are nodes, edges are different properties. Then it finds frequent paths, so the paths on this graph that have large enough supports. Then it uses item set miner to describe these paths as some kind of rules. Then it joins these rules into graphs, and then it needs to see what graphs form good redescriptions. So it builds some kind of a forest of queries. It kind of joins them together based on similarity, and then it computes redescriptions and outputs this kind of graph pairs to the user. And finally, one other work that is connected to the logic itself is that of analysis of time evolving gene expression data by Kleinberg et al. So what they did basically is they had this gene expression data measured in different time periods. So each of these parts is one data set in different time point. They created overlapping windows, then they created clusters in them. Then they redescribed each of these clusters in this overlapping window. They made it overlapping intentionally, so there are connections between time points. Then they redescribed the connections between these windows, and then they discovered that this that each of these redescription sets is basically one world, and the whole set of redescription sets is one Kripke structure. Then they basically have worlds, then they have connections between these worlds, and then they can probably reason in a way more similar to a temporal logic in this kind of with this kind of information. Okay, so this is basically a short overview of redescription mining and its connection to the logic.